In this video, you're going to learn how to draw plane mirror ray diagrams in order to identify images formed by plane mirrors and also to describe the images formed by plane mirrors. So as mentioned previously, a plane mirror is a flat mirror. There are also other mirrors called curved mirrors, which may curve inwards, and some that curve outwards. For plane mirrors, like I said, they're flat, and the scientific symbol for a plane mirror is a straight line with lines at the back to indicate that that is the back, and the part without the lines, so the front over here is the front of the mirror, that will be doing the reflecting of the light to form an image. So plane mirrors and curved mirrors produce an image. What you would commonly call your reflection is actually called your image. You can describe the image formed by a mirror using the acronym SALT, which stands for size, attitude, location, and type. So in this diagram over here, we have an object. That object could be you, it could be anything in front of a mirror. We have a plane mirror, which is a flat mirror, because that's what we're focusing on in this presentation. And then we have the image, which is again what you would commonly refer to as your reflection, but in optics we call it the image. So you can compare the image to the object in various ways. One of the ways is the S in SALT, which is size. The size of the object is represented by HO, which means height of object or object height. The size of the image is represented by HI, which means image height or height of image. You can also describe the image in terms of what's called the attitude, the A in SALT. Attitude is also sometimes called orientation. Orientation basically just means, is the image upright or is it inverted? So as you can see here, we have our object is an arrow. The arrowhead points upwards. In our image, the arrowhead also points upwards. Since the arrowhead points in the same direction, what that means is the image is not inverted, it's actually upright. If our object was an arrow pointing upwards and then our image was an arrow pointing down, then we would say it was inverted. But in the case below, and for plane mirrors, you know it's not inverted. You're not upside down when you're looking at yourself in a flat mirror. Another aspect that you can use to describe the image is something called location. It's basically just how far the image is from the mirror. So we call that DI, image distance, the image of the distance of the image from the mirror, and then the distance of the object from the mirror is the DO. And lastly, an image can also be described in terms of its type, the T in SALT. The type basically just means, is the image real or virtual? If the image is virtual, the image looks as if it's actually in the mirror or behind the mirror. It's formed by these special rays called traceback rays, and we'll get a closer look at that when we do some plane mirror ray diagrams. If the image is real, it looks like the image is coming out of the mirror, or you can actually put the image on a screen. So when I project the PowerPoint onto a screen from the projector, what you see on the screen is a real image because it can actually go on a screen. You could never take an image from a mirror, a plane mirror, and put it onto a screen because the image in a plane mirror is virtual. It forms behind the mirror, and we'll see how that works in just a bit. So for a plane mirror, we're going to describe the SALT characteristics. For all plane mirrors, the height of the image is always the same as the height of the object. So if there's someone who's 5 feet tall standing in front of the mirror, that would be the HO, 5 feet tall. The HI, their image that they see, would also be 5 feet tall. That's always true for a plane mirror. We're going to skip attitude for now and go to location. We'll come back to attitude near the end. Location, again, is the distance of the object from the mirror for DO and the distance of the image from the mirror for DI. If you're standing 3 feet away from the mirror, that's the DO, your image will appear to be 3 feet behind the mirror. So if you take a look over here at this image below, we have the object distance and the image distance, and as you can see, they're equal to each other. So for a plane mirror, DO is equal to DI, and HI is equal to HO. Let's go to type. For a plane mirror, the type of image is virtual. It's not going to be real. The image looks as if it's formed behind a mirror or within the mirror. You cannot put this image onto a screen from a plane mirror. It's also made by something called traceback rays, which we'll get a closer look at in a few minutes. And lastly, we'll go to the A in SALT, which is attitude. The attitude refers to the vertical orientation, so the up-down orientation. As you can see, the flame of the candle is pointing up in the object, and in the image, it's also pointing up. So for a plane mirror, the image formed is always going to be upright. It's not going to be inverted, always upright. Now, we don't typically describe this second type of inversion here, but I will mention it because it is important for you to understand. Even though the image formed is upright, so same vertical orientation, the image is actually laterally inverted. You sometimes think of this as a left to right switch. It looks like your right hand becomes your left hand, your left hand becomes your right hand. That's actually not what happens. It's actually more of a front to back inversion. If you write, let's say, the word optics or the word physics on a piece of paper, and you pick that piece of paper up and you turn the word away from you, but you can still see it spelled through the paper, you'll notice that you've done a lateral inversion. It looks like the letters are backwards, and the letters themselves are backwards, and the words also backwards. So that is what a lateral inversion actually is. It's a front to back inversion. Plane mirrors do that, so do other types of mirrors. But for the majority of your problems, you're going to have to deal with attitude in terms of vertical orientation. And so for plane mirrors, we are simply looking at the fact that the image is going to be upright. So HI equals HO, DI is equal to DO, attitude is upright, and the type of image is always virtual. If you hold a plane mirror up in front of this slide, you'll notice that this word optics will be written in a way that you can actually see it. As you can see in this picture over here, the word ambulance is written in a laterally inverted fashion. Basically, it's written backwards, and that was not a mistake. When you think about it, if you're driving, which eventually you'll be old enough to do, you will notice the ambulance behind you by looking into your mirrors. And because a mirror does a lateral inversion, when you see this word in your mirror, it will look like it's spelled in the correct way. So once again, I just want to go into a bit more detail on the idea behind the image type. In other words, virtual versus real. So in this picture over here, we have an object, we have a plane mirror, and we have an image. You'll notice that it looks as if the image is actually in the mirror or behind the mirror. That's what we call a virtual image. In terms of what that looks like with rays of light, let's go to this diagram over here. A virtual image forms by these rays called traceback rays. Traceback rays are not real rays, they're imaginary. So here's what's happening. We have our plane mirror over here, we have our object over here, and then we have an eyeball here which represents the viewer. So for example, you looking into a mirror. Light rays from the candle travel to the mirror. They hit the mirror and bounce off the mirror. They reflect off the mirror and then go into your eyes. Now, your brain does not realize that this reflection is happening. Your brain thinks that the light rays are actually coming from behind the mirror. It doesn't realize there's a mirror there. You might know it yourself, but your brain can't figure that out. So your brain will perceive the candle coming from behind the mirror. So these rays here are not real. The rays from the candle are actually over here, and they reflect off the mirror and go into your eyes. And because your brain cannot perceive that reflection, perceive that bending of light, it thinks that the light rays are coming straight from behind because light travels in straight lines. So that's what we mean by a traceback ray. A traceback ray is not a real ray. It's a ray that your brain basically fills in the blanks with. The traceback rays are drawn behind the mirror only, and they're represented by these broken or dotted lines. So whenever an image is formed by traceback rays, then we call that a virtual image because the rays are not real. Our brain just perceives them to be there. So once again, here is our summary for the SALT characteristics of a plane mirror. SALT characteristics will vary when we're looking at different types of mirrors, such as concave and convex, but for plane mirrors, they're always going to be the same. The S size, HI, is equal to HO. Image size will equal object size. The attitude, we're going to have an upright image all the time, as you can see over here. The location, DI is equal to DO, so if this is 3 meters away from the mirror, then this image distance will be 3 meters away from the mirror. And again, just to elaborate for height, if this person here is 5 feet tall, well, then the image will also appear to be 5 feet tall. And again, it's a virtual image because the image appears to form behind the mirror, and if we drew a ray diagram, we would see that there are traceback rays. So now we're going to do a variety of sample problems, and these are the problems that you can expect to see on quizzes and tests. The problems include things such as describing images using SALT, and as we've seen, that's pretty straightforward. Simply describing the size, attitude, location, and type. Sometimes you might see a different acronym, LOST, instead of SALT. And so in this case, we have the T stands for type still. L will stand for the location still. S will still stand for size, but the difference is the O. The O just stands for orientation instead of attitude. So if you see LOST, it's the same acronym except the A is replaced by O for orientation. We'll have problem types where you have to find the image. So if I give you an object or a point, you need to draw a ray diagram using those arrows to represent light to show where the image would end up on the other side of the mirror. You need to determine if observers can see an image in a mirror based on their location using ray diagrams. And we're also going to conceptually see what size of a mirror is required to see your entire body from head to toe within it. And then throughout, we're going to see something called the cheat method to make your ray diagram drawing a little bit easier for you. We're going to start off with describing images using SALT. So here's a sample problem that you could see and should try out for yourself. If a man that's 6 feet tall is standing 3 feet in front of a mirror, and I should specify that it's a plane mirror here as seen in the image below, then identify the following: HO, HI, DO, DI, distance of the man from his image, attitude, and type. So HO is given to you in the question. That's height of the object. The man is 6 feet tall, so that's our HO. Now the fact that you know this is a plane mirror allows you to know that the HO has to be equal to the HI. That's our characteristic that we know from the previous few slides. So the HI also has to be 6 feet. We told you that the man is standing 3 feet in front of the mirror. That means that's the distance of the object from the mirror. So that would be, for example, from here to here. And that would be 3 feet. As you know from the SALT characteristics of a plane mirror, the DI is equal to the DO. So the image would also appear to be 3 feet from the mirror. We're going to skip this one for now and go to attitude and type and then come back to that one just afterwards. So again, attitude is, we know that the image is vertically the same orientation, so we can say that this is upright. However, know that it is laterally inverted, front to back. Our type, you can see that the image is formed by traceback rays. So we know it's a virtual image and it appears to be behind the mirror. The last question that I had skipped requires a bit more reading. So the distance of the man from his image. So this is the object, the man, and this is his image over here. So that requires you to think about this carefully. The man is about 3 feet away from the mirror. So that's this distance over here. The image appears to be 3 feet away from the mirror as well, but in the other direction. So the man is 3 plus 3 feet. That's 6 feet away from his image. So read the questions carefully, because sometimes I'll ask you how far something is from their image as opposed to just from the mirror. Here are some more practice problems for you to attempt based on the SALT characteristics that we discussed. You can find the answers to these problems at this website here. It's a really good website that explains all the optics concepts that we're going to see in a great deal of detail, but it's also very, very simple to understand. So I highly recommend using this website when there's a concept that you're not too sure of in the optics lesson, or really anything physics related. So now we're going to take a look how to draw a ray diagram to find an image in a plane mirror. You're going to have to know how to represent reflected rays, incident rays, normals, and traceback rays, as well as the scientific symbol for mirrors. A few things I do want to point out before we get started. When you draw your rays, for example, an incident ray, you need to make sure that there's always an arrow going into the mirror. If that arrow is not there, you will lose marks. For the reflected ray, you always have to have an arrow going away from the mirror and then into the observer's eye or whatever is there, but either way it has to go away from the mirror. If that arrow is not there, you will lose marks. And for traceback rays, you need to make sure that they are represented using those broken or dotted lines. So over here I have the list of steps that are required in order to find an image using the ray diagram technique. I'm going to walk you through a few examples and then I'll show you an easier method near the end. So here we have a single point, and what we're going to do is we're going to try to find its image on the other side of the plane mirror. Now, just to keep this neat, I didn't draw the lines at the back of the plane mirror, but you would normally have to. So our first step to find this image is going to be to make an incident ray of light going from the object to the mirror. And it doesn't matter where you draw that incident ray of light. Once you draw that incident ray of light and it hits the mirror, you need to make sure that you draw a normal. You're going to measure this angle over here, so the angle of incidence. And you're going to use that measurement to find the angle of reflection to draw your reflected ray. Because as you know, theta I is equal to theta R. Once your reflected ray is drawn, you're going to extend your reflected ray behind the mirror as a traceback ray, which was this point, which is this ray over here. So right now we have half of the problem done. We did an incident ray to the mirror, drew our normal, found the angle of incidence, used that to find the angle of reflection, drew a reflected ray pointing away from the mirror. Notice the arrow pointing away. This arrow here was pointing towards the mirror. And then we extended our reflected ray behind the mirror as a traceback. Normally I do the traceback ray even before lifting my ruler. Once I've drawn the reflected ray, I simply extend it backwards behind the mirror. To find an image, you need to have 2 traceback rays, which basically means you need to have 2 sets of incident and reflected rays. So I need to make another incident ray from the exact same point on my object. Okay, so it has to be from the exact same starting point, but it can go in a different position in my mirror. So I'm going to make one ray that goes straight to the mirror, and you'll notice I made it perpendicular to the mirror, which means it's right along the normal. And since it's right along the normal, the ray will reflect back upon itself because the angle of incidence is 0. And all I have to do now is extend that reflected ray behind the mirror as a traceback. The point where the traceback rays intersect, that is the position of my image. Just to prove that, I'm going to do one more set of rays. So I'm just going to do another incident ray from the same starting point, but to a different point on my mirror. I'm going to draw in my normal, 90 degrees to the mirror, measure my theta I, use that theta I there to find my theta R, and draw my reflected ray. And then I'm going to extend that reflected ray behind the mirror, and you'll notice that the traceback rays will all meet up at that one point, and that is where my image will be. If you forget your protractor, a quick and easy way to do this is to remember that DI is always equal to DO. So let's say this distance here was 2 centimeters, while this distance here should also be 2 centimeters. And that way you can find the position of your object on the other side without making any errors. What some people like to do is they simply like to measure DO first, find DI, draw their image, and then do the ray diagram. That's what we call the cheat method. If you do that, I won't notice. So the main point I want you to get here is that in order to find the point of your image on the other side of the mirror, you need to at least do 2 rays per point. So this was one set of rays here. This was another set of rays. I did a third one at the bottom here just to prove that those rays intersect and just to double check that I actually measured my angles correctly. The closer you are with your angle measurement and the more accurate you are with drawing your lines, the more likely that all of your tracebacks will actually intersect and you'll find your image point there. If you can find the image of a point behind a mirror, then you can do the same thing for an object with more than one point. And we'll approach that in the next few slides. So here we have the steps for you to follow in order to find the image of an object on the other side of the mirror, and this was for a single point. So you can attempt this problem here. Again, you can make incident rays go anywhere on the mirror as long as you are following the law of reflection when you make them reflect. One of my favorite rays to do is one that's perpendicular to the mirror, because all that really means is that it reflects back on itself, and then I can do my traceback ray directly behind the mirror. I'm not using a ruler here. You would have to use a ruler and a protractor. I'm just doing this quickly to show you the general idea. You can do another incident ray from the same point on your object to the mirror, draw your normal, measure your theta I, use that to find your theta R. And again, because I'm not using a protractor or ruler, I will be off, but I'm just showing you the general idea. Before even lifting your ruler, extend the reflected ray behind the mirror as a traceback ray, and the point where they intersect, that's where your image would be. If you measure the distance, this distance here, DO, should be the same as this distance here, DI. We have a virtual image because it's made by tracebacks, and if we could measure the height, it would be the same height. HO would be equal to HI, and it would also be the same orientation if we could show the orientation of this dot. You should be able to do the same thing for any dot that's given to you, any point that's given to you, because it's always the same concept. Again, always use 2 rays per point, and one of the best rays to use is always that perpendicular one to the mirror, because it reflects right back on itself and it doesn't really require any angle measurement other than knowing what's perpendicular to the mirror. Same thing here, another point. You can do 3 points at once, so you'd have to do the same idea that we did in the previous slide. So go with 1 point at a time here. So incident ray from this point to the mirror, draw your normal. Make sure that arrow shows. If it doesn't show when it hits a mirror, make sure you draw the arrow in the middle. Measure this angle here to use that to find this angle over here. Make sure you have the arrow pointing away, and then draw your traceback ray. Do the same thing here. I'll do the one that's perpendicular to the mirror, bounces right back on itself. Make sure you show that. Then do your traceback ray. And the point where they hit, that's where your image is going to be. Do the same thing for this point here and this point here. Try to aim the incident rays so that they don't hit the rays that you did for this point, just so that it doesn't get too messy. It's always good to have a nice sharp pencil and eraser when you do these type of problems, because things can get messy. And always have your protractor and ruler with you. You will lose marks if you're not drawing nice straight lines. Again, don't follow this example. I'm giving you the general idea. You need to use a ruler and a protractor. So you probably guessed it. If you can do 3 points like this, then you can probably do an entire object rather than just a single point. So let's say you had to find the image of this arrow in your mirror. What you would do is you would start off by defining the object by 2 extreme points. So I would put a point on top here on the arrow head. And I would put a point at the bottom here, the arrow tail. And what I would simply do is you could really find any point along this arrow that you want as an image, but there's no point in doing that. Just find the extremes. So I'm going to start off by doing the ray diagram for the top. So I'm going to do my incident ray that's perpendicular to the mirror, and do measure to make sure that that is actually 90 degrees to the mirror, otherwise you will be off. It reflects back on itself since the angle of incidence is 0, and then do your traceback ray. Again, before you do this, you can actually measure DO and DI and make sure that your image is the correct distance away. Just draw it beforehand, and then afterwards do your ray diagram. Like I said, I won't know. Okay, but that's not enough. We need to have an intersecting point, so I'm going to do a incident ray that goes from our arrowhead again, but this time hitting the mirror at a different angle. Show that arrow going into the mirror. Draw your normal 90 degrees to the surface of the mirror. Measure your angle of reflection, of incidence. It's your theta I. Use that to find your angle of reflection. And extend your traceback ray behind the mirror. This here is the top of your object. So let's call that top of our object AO. Or rather, I should say this here is the top of your image, so we'll call this AI. That's the arrow head. And again, what I want you to do on these ray diagrams is fill in all the information. If you find theta I, write down what theta I is. If you find theta R, write down what theta R is as well. So great, we found the arrow head, but now we need to do the same thing for the arrow tail. So I'm just going to choose a different color to do that in. Let's choose blue. Same idea. I'm going to do the incident ray that's perpendicular to our plane mirror. Show that arrow. It reflects back on itself. Extend my traceback ray behind the mirror. Then I need to do another incident ray. It doesn't really matter where I do it. I just don't want it to maybe interfere with my red ones. So I'm just going to make it go down here. Draw my normal. Measure my angle of incidence. Use that to find my angle of reflection and draw my reflected ray pointing away from the mirror. And as you can see here, I am a little off because I'm not using a protractor and ruler, but you will be. Draw your trace back ray behind the mirror. That's the arrow tail. Then you can actually draw your image in. So connect the two dots and make sure you know that this is an upright image, so your arrowhead should be pointing upward still. We'll call this second point we did here BO, and therefore the point we just found was BI, point B of the image. If you had a triangle, you do the same thing. You do one for one, you do two sets of rays for one corner, two sets of rays for another, and two sets for the third. And then afterwards you'd connect all your dots once you found them. I like to label the points on my object so I know which point on my image I found, because otherwise it can get confusing, and you do need to show that arrowhead to show that you have an upright image. As you can see, our HO is equal to our HI because we have a plane mirror. Our DO is equal to our DI. We have a virtual image because it's formed by trace back rays and it's behind the mirror. And as mentioned earlier, the attitude is an upright image. You can do the same for this object over here. Define your 2 points, AO and BO. And then do the whole series of steps all over again. If I ask you for HI, DI, DO, HO on a test or a quiz, you should have a ruler with you because I would expect an exact number. So if you measure something to be 2 centimeters, well, that's your HO. If you found the image to be 2 centimeters, that's your HI. If you get a problem like this, you need to be careful. Some students will take this arrow here, label it AO, label it BO for the second point. They'll make an arrow that goes straight to the mirror and they'll think that this is one that's perpendicular to the mirror. It's not. Make sure that you realize that. You would do the same steps though. You'd use your protractor to find out, to draw your normal. The normal is perpendicular to the mirror. Again, perpendicular meaning 90 degrees. Find your theta I. To help you find your theta R. And then do your trace back. The mirror in this case is slanted, so don't be fooled by that. You can try to do a ray that is perpendicular to the mirror. It reflects back on itself. And then you can extend that backwards, and then hopefully it meets. Now, as you can see, mine probably won't meet because I didn't really use a ruler and didn't measure angles properly. But if you did, you would see they would meet, and that would be your AI. So I want you to try this one, attempt it. I want you to compare it with some that your friends have done, your peers have done, to make sure that you can do any type of finding an image in a mirror problem. It really is always the same steps over and over and over again. You just need to make sure that you use a proper ruler and protractor. Otherwise, you'll make a mistake, just like I did on this slide here. Same idea, you should attempt this problem to make sure you can do any type of ray diagram problem. Always the same steps. Make sure you show those arrows. Make sure that you draw in your image. Make sure that the incident ray goes into the mirror, the reflected ray comes out of the mirror. Make sure your normal is a dotted line. Make sure you show the angle of incidence and the angle of reflection. Try to create a checklist so you know what you have to include in each ray diagram. And as I mentioned previously, if you had an object with more than 3 points, make sure you label those points. AO, BO, and CO. I do want you to try this one here, especially because this one will illustrate the idea of lateral inversion. You'll see that there's no upright inverted type of inversion, but there is a lateral inversion. So do try this out so that you can prove the idea of lateral inversion. Now we get to our third type of problem, which is determining if an observer can see other people or objects, or other people or object images in a mirror. And so this is basically the same type of problem as we saw just previously with the ray diagrams, but we're working backwards. So sample problem together. Here's our sample problem. We have an object, and this over here is the image of the object. And so the question is, can the observer see the image of that object? So here's what we do. Line the image up with the observer's eye. From the image, draw a traceback ray that heads towards the observer's eye, and that traceback ray needs to pass through the mirror. Now, once it hits the mirror, the traceback ray becomes a reflected ray, because a traceback ray is really just an extension of a reflected ray. Draw in your normal, and then draw in your incident ray according to the law of reflection. If you can draw a traceback ray from the image to the eye through the mirror, then that means that the observer is actually able to see the image. If you can't, then the mirror is not long enough, or you need to change positions in order to see it. So let's say we're looking at this image over here. You'll notice I try to draw a traceback ray from this image to the observer, and I can, but the thing is that that traceback ray does not go through the mirror. That means that this observer cannot see the image from this position. The mirror might have to be moved or extended in order to see it. So let's do a sample problem here. The question is, who can see what I see? So this side over here, the bottom part of your screen, is going to be the front of the mirror. The top part of your screen is going to be the back of the mirror where the images are. So again, we want to see who CY can see. So let's take a look at this image over here. CY is a person. We're going to see if we can make a trace back from the mirror, or from DI is images all the way to CY. So we made a trace back here. Once it hits the mirror, it has to become a reflected ray. Remember, since it's a reflected ray, the ray goes out of the mirror. Draw normal. Now, this image, DI, is the image of DI over here. So rather than measure the angle over here again, I can simply draw my ray heading towards DI, because I know it must have come from DI over here to make an image of DI behind the mirror. Now, because this is an incident ray, it goes into the mirror. We're working backwards. You trace back, reflected, incident, as opposed to incident, reflected, trace back this time. So we know that CY can see DI. Well, let's see who else CY can see. Let's see if CY can see him or herself. make a traceback ray, hits the mirror, becomes a reflected ray, goes to CY. So because you can make a traceback ray from CI image to CY that goes to the mirror, then CY can also see DI. Let's see if CY can see the image of Ed or EI. So this is Ed over here. This is Ed's image. So can we do a traceback? Okay, it becomes a reflected ray now. And we know that that ray initially came from Ed. And we can put it in our normal. So CY can see C, D, and E. Let's see if CY can see BI. So let's try to make our trace back. Let's choose a different color here. A trace back from B to C. You'll notice if you use a ruler, you can make a trace back, but that trace back will never go through the mirror to CY. So that means that CY cannot see B. Same idea with AI. CY cannot see AI. Let's see if CY can see Fred. No, it doesn't look like CY can see Fred. Let's see if we can do a trace back. So the traceback does hit the mirror, but if you keep going, it does not hit CY. So because the traceback, even though the traceback does go through the mirror, it still won't reach CY's eye. So CY either needs to move or the mirror needs to be extended in order for CY to see that image. So CY can really just see C's image, which is his or her own image, DI's image, and Ed's image. And again, all that's required of you to do is to draw the tracebacks from the image towards the observer. If the tracebacks can actually turn to reflected rays and reach the observer by going through the mirror, then that means that that observer can see that image. So CY can see those three individuals. You can try this again by this time attempting to determine who DI can see, or even who Fred can see, or even who Ed can see. And you can try the same thing for Al and Bo. Again, anything below the mirror on the bottom half of your screen, those are the objects, the people, the observers, and everything on the top half of your screen, those are the images. So top half images, bottom half observers. So try the same problem here to see who Fred can see. Do the trace backs, see if they go through the mirror. If you need to see the answers or do an interactive, the answers are on the Physics Classroom website at the link above. Again, I do recommend that website when you're learning optics. Attempt the same problem, but from Ed's perspective this time, and the answers are in the link below. Based on the problems we just did, you should be able to answer a question like this. Can the observer see the entire image? So in the case like this, in a question like this, what you'd have to do is you'd have to figure out where the image is first. And I don't mind if you use the cheat method. So basically just measure the DO of both extremities, and then find your image on the other side and draw it. Make sure it's the same height and distance away. Now I didn't do this with a ruler, so I'll be a little bit off. So what I want you to show is if the eye can see the entire object. So what that basically means is you have to make 2 points, or the entire image rather. 2 points, one on the top of the image, one at the bottom. Do a trace back from the top of the image to the eye. Turns into a reflected ray once it goes past the mirror. Draw your normal. And then make your incident ray from the top of the object, because that's the top of the image. The fact that the traceback ray was able to go from the top of the image to the eye indicates that the observer can actually see the top of the image. Let's see if the observer can see the bottom of the image by the same concept. So I'm just going to use a different color to show the bottom of the image concept. Let's use blue. Make a trace back from the bottom of the image towards the eye. Once it hits the mirror, it becomes a reflected ray. Make your normal. And make your incident ray from the bottom of the object, because that was the bottom of the image. And make sure they all connect. Again, because you're able to do a trace back through the mirror to the eye, that means that the observer was able to actually see the entire object from head to toe, or from top to bottom, so from the arrow to the bottom. Now, one more important concept that for more information, you'll notice there's an area of the mirror here that's flanked or surrounded by your trace back ray intersections, trace backs from the top and trace backs from the bottom of the image. This area of the mirror is actually the only part of the mirror that you really needed in order to see the entire image from top to bottom. The rest of the mirror is really just extra mirror that you don't need for the position that you're at. You can do the same problem for this mirror over here. So now we're going to finish off by taking a look at this riddle for the day. What distance away from a mirror must you be in order to see your entire body? So what I want you to do is find a plane mirror in your home and just look straight ahead and see how much of your body you can see in that mirror. And what I want you to do is back away from the mirror until you can see your entire body. Even if you have to head out your front door, keep doing it until you can see your entire body from head to toe. So entire body by definition means head to toe. You could walk as far back as you want. You'll never actually be able to see your entire body from head to toe if your mirror is not large enough. The distance doesn't matter. What matters in this case for a plane mirror is size. To see your entire body from head to toe, there are two conditions required of a plane mirror. The first is that the size of the plane mirror, or the height of the plane mirror, has to be half of your height, at least half of your height. So if you're 6 feet tall, the mirror needs to be 3 feet tall at least. The next condition is that the mirror has to be held at half the distance between your eye and the top of your head. So basically in the middle of your forehead. You can actually observe this ray diagram to illustrate that concept. Here we have a large mirror, and I did the same concept of can the person see the entire object from head to toe that we saw in the previous slide. Trace back rays from the head all the way to the person's eyes, trace back rays from the feet all the way to the person's eyes, and then we can see these trace back rays from the bottom and top of the person crossing through the mirror. This portion of the mirror here is all that the person requires in order to see their entire body from head to toe. It doesn't matter what distance they're at. They will be able to see their entire body from head to toe as long as this portion of the mirror here. And that portion of the mirror would be about half their height. So if this person, again, like I said, is 6 feet tall, that's their image rather, but this person is 6 feet tall, well, this portion is going to be 3 feet tall. So two conditions: mirror has to be half your height at least, and the mirror has to be basically between your eyes and the top of your head, so near your forehead. So based on that concept, you should be able to solve a problem like this and challenge yourself. You can even explain this problem using a ray diagram like we saw in the previous slides. So what we saw in this presentation was how to draw ray diagrams for plane mirrors. Plane mirrors are extremely important in everyday life. You do need to know some applications of those plane mirrors as well as curved mirrors, but right now we're going to focus on the plane mirrors. I do want you to read up on them in your textbook in some detail. I'll go through a few just briefly, but I want you to be able to use ray diagrams to explain how those applications work. One of the neatest applications of plane mirrors is in something called a periscope. It basically allows you to be a spy. Essentially what happens is you have plane mirrors set up in a box. Light from whoever you're trying to spy on enters that box, bounces off a plane mirror at the top, and then it bounces off a plane mirror at the bottom, and then into your eyes. So that relies on the laws of reflection in order to reflect light from some object that doesn't know you're spying on them into your eye. You can even see that used in applications such as the periscope of a submarine. There's also sometimes lenses applied in this system, but right now we really just care about the plane mirror that's used. Another interesting application of plane mirrors is actually stealth technology. So a lot of planes who need to go on stealth missions, who want to avoid being seen by radar, will actually have plane mirror-like surfaces, which will help to deflect some of the light rays away from the radar that's trying to detect them. So if a plane was shaped like this over here with more curves in it, when a light ray hits it, it bounces right back into the radar antenna, and then you basically told the enemy that you're approaching. However, if you have more plane mirror-like surfaces, when a light ray hits that surface, it's going to bounce off according to the law of reflection in a different direction at the same angle, but it won't go back towards the radar detector antenna, and therefore you will have avoided being detected, and then you can plan your surprise attack. The rear view mirror in a car is a plane mirror. The main mirror in your bathroom usually is a plane mirror, so you can get an image that's the same size as you, that's also upright. You wouldn't want to be applying makeup or fixing yourself up by looking at an inverted image. That might be a bit difficult. Sometimes you'll also see these plane mirrors in clothing stores when you're trying on new clothes because you want an accurate image of yourself as opposed to a distorted one. You wouldn't want to see a funhouse mirror representation of yourself when you're trying on new clothes. It probably wouldn't bode too well for the clothing industry. So in addition to completing the learning goals for the plane mirror presentation, you should also do some readings in your textbook if you really didn't understand the concepts that we saw in this presentation. Some good practice problems to attempt are those on page 493, numbers 1 to 9, and then also 11. 9 is a very good conceptual question that deals with the size of mirror required to see your body from head to toe. And again, do complete as many practice problems and worksheets as you can involving ray diagrams for plane mirrors. You need to make sure you have the protractor and ruler with you at all times in order to provide an accurate answer to the questions you'll see on quizzes, tests, and homework.